And they include statistical inference. That's a big one. What else? With proper sampling, this will make sense in a minute, that's why I put in quotations. A finite sampling, without replacement sampling, called without replacement. Infinite population sampling, which will make sense. I want to make sure you know the difference between finite and infinite. And then know the difference between simple sampling and stratified sampling. Know the difference. Stratified is dividing the samples, the population into subgroups. That's what stratified is all about, stratus. Breaking into subgroups. Statistical inference, you're going to learn about how important it is to have sample sizes 30 or above. Now, we're with the new equation. I've been hyping it up the whole semester saying we're going to be switching to this equation where you got to take the sample size into consideration. That starts this week, all right? The sample size could be a 1, which is the old equation, which is then just divided by standard deviation, but almost you can expect the whole homework, which I'm about to show you, to all have sample sizes more than 1 now. And so you've got to use this new equation. The square root of the sample size divided into the standard deviation. This is now, the denominator is no longer just the standard deviation. It's now called the standard error. As a matter of fact, it's really called the standard error of the mean, and we're going to get into, in a week or two, standard error of the proportion. But this one's called standard error of the mean. This is the one we're focusing on. You've seen this formula a bunch of times. The number you're being asked about, minus the mean is your numerator. I put it in parentheses because order of operations says you've got to subtract that before you divide. Take the standard deviation divided by the square root of the sample size. Then the last step is to divide the denominator into the numerator. That's the last step. That's the order of operations, or you won't get the right answer. All you're calculating at that point is z. This equals z. Now, let me show you your homework, because this will make sense in here. Whoop, whoop. Whoop, whoop. Come on, almost there. Here it is. The homework assignment is called Written Excel Assignment, and it's due a week from today, Tuesday, April 2nd. Usual materials, blah, blah, blah. Whoop, whoop. Here it is. 1A. It's asking you to show your detailed work manually calculating the z-score. Manually calculating the z-score. That's what you're doing right here. Then it says, then give the norm S distribution. This is review. Norm S distribution, parentheses z. Let me repeat this. Every one of these A's are doing the manual equation to find z, which includes that sample size. Then using norm S Excel equation to find the result. So you're showing me this setup, you're showing me this calculation. Once you got z, you're plugging it into either a norm S distribution z or 1 minus norm S distribution z, and give me the result. Some of you like to use norm dot S dot distribution, which then you got to give the z, comma, and a 1 on the end, meaning cumulative. So I just want to make sure you realize that. If you use the dots on this, you have that extra number. All right, and then this is a review also, because all the part B's are asking you to solve the part A's again, but use the Excel equation, norm dot distribution. These are the B's, and we've done these before. Here's the difference though. The first number has always been the number you've been asked about, to find the probability of. The second number has always been the mean, but now the third number is not the standard deviation, it's the standard error. This whole thing. And you don't need to calculate this. You can type that whole thing in there as the third number. You just put standard deviation, put a line that means divide, then use the command you learned last week, SQRT, which is square root, parenthesis, the sample size, parenthesis. And that's what you're going to put there from now on, is that whole equation, comma 1. Because we always use a 1 with normal distribution. It's always cumulative data. So these are review, but the first equation with the norm S is for part A of every one of these homeworks. The second equation is for part B. And the only difference between this and the homework you had back in week 4 is that standard error now has to be used with the sample size. That's the big change. So let's look at how many we got here.
1A, do it manually, use norm S. 1B, give the Excel function equation, which is that norm dot distribution, excuse me. 2A, solve it manually. 2B, give the Excel equation and result, all of these. 3A manually. 3B, give the Excel equation and results. Let's see how many we got here. 4A, 4B, 5A, 5B, 6A, 6B, 7A, 7B, a little change here. Here's the change. Says, find the probabilities that the sample mean is between 33 and 35.5. Okay, here we go with between two numbers again. If anything, we just learned on the quiz that if you're being asked between two numbers, to treat them as two separate questions, if anything. I mean, if you remember how to write the one long equation for both of them at the same time, that's great. That's really what I'd like to have. But at least remember to treat them as two separate equations if you can't remember the long equation. Because you could find the probability of 33, find the probability of 35.5, then take the bigger one minus the smaller result. Whatever the bigger result is minus the smaller, so you get a positive answer. And you could do it that way. So anytime you see these between questions, consider doing them separately if you can't remember how to do them all in one.
For the equations on the board, it's one used for less than and one's for more than? Or
No, vice versa.
Okay.
She's asking about the one minus in front of these equations, right?
Mm-hmm.
Yeah, again, these are not like exponential, well, Excel equations, even exponential, always have the one minus for the more than. It's the manual exponential that you have the one minus for less than and two one minuses for the more than. But that's only when you're doing exponential manually, and that's the only one. All the Excels, even exponential, even binomial, even Poisson, all have the one minus in front for more than questions. Only the more than. So 7 is like two questions in one because you got two numbers there, 33 and 35.5. And yes, you're gonna manually do them separately. Do this whole thing for 33, do this whole thing for 35.5. Get two Z's, do two norm S distributions, make them both less than, so no one minus in front. Get two results, then subtract the two results. That one right there is probably worth more points than the other ones because you gotta find the probability between two numbers. Here's the bad news, there's even a number 8, which is also between two numbers, 149 and 144. So you get, and that's the end. You got 8 of them, which is really 16 problems. And then you have 2 of them that are really like 2 problems in one, so now you're at 20 problems. You finally might be giving me an hour. Finally. Wow, I can't wait to hear from you on Thursday. Well, nobody will be done on Thursday. I can't wait to hear from you guys next Tuesday. Tell me if it took you an hour finally. Yeah, without that beard, it feels like a whole new student here. I don't even know who you are. I'm not even sure you're in the right room.
It'll be back next week.
Okay, that's all it'll take is 1 week, it'll be back?
Yeah.
Okay. Get your passport picture first. And then roll it back. All right, that's all I got on that. Let's get to the other stuff. I don't know. Okay, I'm gonna refresh your memory. We've talked about this in the past, about randomness, how important randomness is, because this all leads to statistical inference. This statistical inference is all about inferring something about a population based on what you discovered from the sample. But it doesn't work if you don't do the sampling correctly. Now, I don't know if you remember this story. This is why I brought this up. I'm trying to refresh your memory of this story. We've talked about this a couple different times where, okay, we're the admissions office. You guys are the director of admissions. We have 900 applications here. These are all we're accepting of these 900 students. We haven't got them on the computer yet, but we gotta go to this meeting, right? And we gotta report the average SAT score, mean SAT score. If you recall, we said, okay, we're gonna take a sample of 30 of them out of the 900 and find the average SAT score for those 30 and infer that probably then the average SAT score for all 900 will be close to this. That's called inference. Being able to make that inference from the sample to the population. But inference doesn't work if you don't follow the rule on good sampling. Here's the kind of the golden rule. If every population item has the same even chance to possibly be picked as one of the sample, that's how you do random sampling. As long as every one of them in the population had a fair, even shot at possibly being chosen as part of the sample. That's the key. And then you can apply inference. The other key is that the sample size, kind of a golden rule, and don't be wrong, we're gonna have a bunch of problems where the sample size is not 30 or larger, but to infer things, you should always have a sample size about 30 or larger. That's kind of a golden rule in statistics also. All right, so let's pretend we have these 900, and we're doing 30. We gotta get 30 out. We numbered them from 1 to 900, and we're gonna use Excel to pick our 30. My question for you is, this is review, I think this is from last week or the week before, I think last week. Should we use ran between or ran parentheses parentheses? Which one is used with which kind of data? And which one should we use to pick 30 out of these 900? Ran, which ran? Ran parentheses parentheses?
No, the first.
This one? This one? This is the one used with, I wanna make sure I say this right, discrete data. 1, 2, 3, 4, 5. We numbered these applications 1 through 900, so they all have discrete data numbers on them. I didn't number any of them 5.5, I didn't number any of them 262.2. They're all got solid numbers, so this is the one we would use. If we're trying to find random numbers of any of the numbers between numbers, you know, discrete or continuous data, we use RAND parentheses parentheses. It's not as important how to use RAND parentheses parentheses. Instead, I want you to focus when to use it. If there's a question about this, the difference between these, it would be when do you use this? With continuous data. That's when you use it. When do you use this? With discrete data. 1, 2, 3. So sure enough, we use ran between. We put the first number at 1, the last number at 900, because we numbered them 1 through 900, and we let Excel give us our numbers. So here's the numbers we got. Where are they again? There they are, 744, so we pull out number 744. 436, we pull that one out. And so on and so on. 902, well there's no 902. Obviously they were using a page of random numbers, so we weren't, because if you use this, you would never get the 902. So they were using random numbers maybe. Since that's not, you just keep going until you have 30 good numbers, 30 applications pulled out. If a number gets repeated, the application's already been pulled out. So you just keep going until you get 30. And they kept going until they got 30, and here they are. Here's all the SAT scores. Now we're gonna add all 30 SAT scores, we're gonna divide by 30. Oh, there's ran between, there you go. And there it is, 997. And now we're going to this meeting and we're saying, hey, here's the deal. I don't have all the applications on our system yet. We did a random sampling of 30. We added the SAT scores, divided by 30. We got 997. I can tell you, with statistical inference, I can infer that most likely all 900 of them, if we could find the average right now, it would be pretty darn close to around 997. Because of the sampling process we used, gave all 900 a chance to be one of the 30. And then the housing director's there, wanting to know how many are gonna be in housing. Out of the 30 that were chosen at random, 68%, 20 out of 30 of them said, yes, I wanna live in student housing, which is 68%. So out of 900, multiply it times 68%, around that many are probably said, yes, I wanna live in student housing. So housing director, prepare for whatever 68% of 900 is, right around that many. So now, we get all 900 put in, and we find out the true SAT mean score and the true percent of those that said, yes, I wanna live in student housing. And we get, let's see, our estimate was 997, it was 990. We're only 7 off, that was pretty good. We estimated 68%, hey, housing director, it was 72%, that's just a few more. But still, darn close. That's what inference is. Inference says if you do random sampling correctly, good random sampling, you can find some stuff out about the population from that sample. It works all the time. And it's all about the sampling process, yes.
How did you get 997 again?
997, I went ahead and took a random sample of 30 of them, added their SAT scores and divided by 30 and got 997. So there it is out of the 30, but when we did all 900, it ended up being 990. So our sample was a little high, but very close, still not bad. And then the same with the 30 of them, we counted out of 30 how many said, yes, I wanna live in student housing, and that was 20 out of 30, so that's 68%. When we put all 900 in the system, it was actually 72% yes, I wanna live in student housing. So the student housing director from that meeting prepared for 68% of 900. Now we give them a call, we say, hey, we got them all in the system now. Instead of 68% of 900, it's more like 72% of 900, so prepare for that. But it's they're so close to each other, it's like, it's no big deal. We told them at the meeting that this was an estimate. But look how good of an estimate it was, this is a PowerPoint, so who knows really. But that really is how well it works. Statistical inference, it really does work that well. All right, so now, let me get better with the definitions here, let me keep going. Going all the way back to slide 2, which really defines inference for it. It says, statistical inference is to obtain information about the population from information contained in the sample. That's right, the information from the sample will give us some ballparks of some information about the population. What I want to point out here is, go ahead, I'm sorry. What I want to point out on this next slide is, proper sampling methods are the key to be able to do inference. With proper sampling methods, the sample results can provide good estimates of the population characteristics. But that's the key right there, and that's why I have in parentheses here. With proper sampling methods, that is the whole key of how statistics works and why it works. We live in a world of randomness, and statistics only works because we live in this world of randomness. And it works every time. All right, I don't know, that just put a dent in anybody's mind for anybody. Now I want to go to finite. I want to go to slide 6. Let me make sure you understand a finite population, what that means. Those 900 applications at the admissions is a perfect example of finite population because we have 900. We're not taking any more applications. We've accepted 900, we have 900, 900 have accepted our invitation to admit. There it is, the population's 900. Finite because no more are being added to it. That's what makes it finite. I'm gonna talk about infinite in a minute, but I'll make sure you realize what finite is. Here's examples. Organization membership roster. There's this many members, we don't have any more members coming right now. This is the list of members. Let's number them 1 through however many are there. Now we can take a sample of our members. That's a finite population. Credit card account numbers. Right now, the credit card company only has so many credit card account numbers. This is it. We're going to sample out of these, and then that's what a finite is. All right, so we got that. Now, let's go to what's called sampling without replacement, which is what I want you to remember about it. Sampling without replacement is the most common sampling done, and the ones I've witnessed have been in the auto industry. The example is we happen to, in Southeast Michigan, have a bunch of auto suppliers that provide the auto industry with parts that they manufacture off-site in their business. Let's say this place does just brake pads. They're providing the auto industry with brake pads, and they're a supplier. Well, when they get a load of brake pads made, they call, let's say they're selling them to General Motors. They'll call General Motors and say, okay, we're about to ship these brake pads. We've got 10,000 of them ready to go. Your order's been filled. And then General Motors says, okay, we'll send quality control right over. This is how it works. Quality control comes over, sets up their laptop and their machines that are measuring something about those brake pads. Something that's been agreed upon in a contract, that they're supposed to be exactly blankety blank thick, or they're supposed to be exactly blankety blank wide, and the holes are supposed to be exactly blankety blank circular diameter, or something like that. There's some specifics that the quality control is gonna measure. They put these brake pads, they randomly select, there's 10,000 brake pads sitting on this dock, randomly selecting 30 of them, putting them through this machine, boom, boom, measuring something, all being recorded. Another one, here's 30 of them done. Now we're getting the mean measurement. And the agreement is that mean measurement is supposed to be at this amount, or 1 standard deviation or 2 standard deviations above or below it, and that's it. And if that mean, and then the person says, okay, got one, now I'm gonna do it again, and picks 30 more at random. But the point I'm about to make is, that original 30 did not get put back in. Everybody hear that? The original 30. And this person will do this about 5 or 6 times, picking 30 out. That's called sampling without replacement, which is the most common. Had that person taken those 30 from the first batch and mixed them in with the 10,000, some way of mixing it up, then picking 30 more, that's also a good random technique. That's called sampling with replacement. But the most common that I've experienced and that I've read about have been sampling without replacement. That's more common, because of the amount of time and work it is to put them in and try to mix them up with the other 10,000. When you have so many, you don't have to replace them. You pick a new batch of 30. So that's the difference with sampling without replacement. And the thing I want you to remember the most is, without replacement is the most common. All right, next, and I'm going to slide 8. I wanted to point out a couple things here. Here's another situation where sampling from a possibly very large population when it's not possible or perhaps feasible to identify all elements population. All right, so what they're saying is, let's say we have a population of not just 900 applications, but whatever it is that this population is, there is maybe 50,000 in the population. And there's no way for us to number 1 through 50,000 because there's just so many of them. Whatever this may be, whatever, we can go ahead and use applications for some college, but 50,000, try to imagine. And that's where numbering them and then using random between to know which one to pick out won't work. So you gotta come up with a different sampling technique. And that's all I wanted to point out, is that sometimes applying random numbers to every item in the population so you can pick 30 out doesn't always work, because there could be too many there to be able to number them all. And then you gotta figure out a different technique to use, whatever it may be. Whatever the technique is you decide to use, it will, when you go to get published, other researchers are assigned then to duplicate your research. And your technique, whatever random technique you use, they have to duplicate it to make sure it truly is a technique that will allow everyone in the population to have an even chance to be part of that sample. That's the key. So anyway, I want to point out that sometimes you can't use numbers. That was slide, okay, now finite. Here's finite right here. Oh, I'm sorry, infinite. We did finite. Here's infinite. And an example of an infinite population is where the population keeps changing. A manufacturing process that goes 24/7 has 3 shifts, and they keep adding to the items that have been made that need to be inspected. That's called infinite population, because it keeps changing, keeps getting more added to it. What's it say here? In this case, infinite population, is impossible to obtain a list of all the elements in the population. A simple random sample of infinite population is a sample selected such as the following conditions are satisfied. When you have an infinite population, it's a little more difficult to do the sampling. So you have to make sure each element selected comes from the same population, and each element is selected independently. Those are the keys. It's not so much of you numbering them and then getting 30 of them out. It's maybe a different process, but at least it has to adhere to these 2 parts of it. That each one you pick out is done independently and not grabbing up 30 at one time or anything like that. That's part of it. All right, let me look. That's all I have for definitions. Now I was going to start getting into examples, but I noticed I wrote a note to myself that I'd rather get into all the math at one time on Thursday. And Thursday is all about preparing you to do that homework assignment, showing you exactly how to do it manually and how to do it using Excel and getting results. So that's what we're doing on Thursdays. Anybody have any questions about the multiple? Don't forget, what I just talked about, all those definitions there, was preparing you for probably several multiple choice questions for the final exam. So that's how you should look at that. All right, I'll see you on Thursday.
No way, man.
I thought you were gonna stop it. You look like it.